given as 5. Anybody completed this problem? Have you got the results? Yes. This is the value of J and D.
Sir, is it J and D or J and B, sir?
The voice is not clear. Can you put in the chat box? Okay, then we'll continue. So, in order to get this value, first of all, we need to derive the transfer function of the system, right? So, this will be T of theta of T, this is also theta of T, right? So, by applying Laplace transform, we can write this as theta of S divided by T of S is equal to 1 divided by J S square plus BS plus K. So if you take J common out, you can write 1 by J divided by S square plus B by JS plus KJ, right? So if you compare with the standard form of a second order system, what we can write? We can write, sorry, so what is omega n? Something? Yeah, omega n equal to root K by J, and 2 zeta omega n is equal to B by J. So given, what are the things given? Percentage overshoot is equal to 20%, and one more parameter is given, right? Yeah, settling time is given as 2 seconds. So from this we can find zeta and omega n, right? So from the known information. So we know the equation of MP means peak overshoot. Peak overshoot is equal to, what is the equation for peak overshoot? E power minus zeta pi divided by root of 1 minus zeta square into 100, right? So we can, this is given us 20%. So we can write minus zeta pi by root of 1 minus zeta square is equal to natural number 0.02. Can you find and tell me what is the value of zeta? What is zeta?
Zero point 0.4559, sir.
Actually, your voice is not clear for me. Maybe because of some network issue. Can you put in the chat box that value alone, whatever you got? I think values are not D. 0.45, yeah, fine. That, yeah, 0.4559, right? Yeah. 1,455, yes, fine. Where I mentioned it is the in chat box, someone must comment. Where I mentioned? Ah, yeah. Yeah, right. Yes. Okay, now we have zeta. Now what we can do is find the yeah. Now we need the omega n, right? So in order to find the omega n, one more parameter has given, it is settling time, right? Settling time is equal to 2 seconds. Since nothing is mentioned, means band is not mentioned, you assume the band is plus or minus 2%. For plus or minus 2%, what is the time constant? It is Ts is equal to 4 times T, where T is 1 by zeta omega n. So from this, this is given as 2 seconds. So you find omega n is equal to 2 divided by 4 multiplied by zeta is 0.455. So what is omega n from this? Please put in the chat box. Some issues there with voice. The value I will put in there. 4.386. Okay. If any mistake is there, tell me, because I don't know the exact result. 4.386. 4.386 radians per second. So if you know zeta omega n, we can find omega n, right? Sorry, we know omega n is equal to root k by j. K also given, right? So you can directly calculate the j. We calculate all the parameters certainly. Omega n equal to root k by j. From this, we can write j is equal to k divided by omega n square. K is given, right? I think what is the value here? 5 Newton meter. So it is 5. Every unit also 5 only, right? 5 Newton meter per minute. So we can write 5 divided by 4.386 the whole square. So it will become, what is j? Is it 0.26? No, not clear for me. Yeah, 0.259. Yeah, fine. No, yeah, correct only, right? Now what we have to do is you have to find the value of b. So how much you are getting for b? Because b can be found out from this relation, right? Yeah, this one. If you substitute in this, you can find out b. So what is the value of p? 1.039. Yeah, fine. 1.03. Okay, clear. So this is the pattern. So we for this particular system, the zeta is obtained as 0.456. So it is a underdamped system. So first there will be oscillations, overshoot, undershoot. Finally, after a settling time, it will reach the steady state value. Okay, so we will wind up the second order system here. So one thing keep in mind, this first order system and second order system is very, very important. Okay, so hope everyone understood the concept of zeta, the importance of zeta in the second order system. So if you have any doubt, you can ask later also. Okay, so we will move to another topic in the second unit. Analysis of steady state error. Analysis of steady state error. Okay. Okay. So first of all, I'll draw the closed loop block diagram for a negative feedback system. So this is R of S. Let it be the input plus I have forward path gain G of S and I have an output Y of S. This is feedback to the input through a gain block H of S and is reading from the output, right? So this is a general block diagram of a closed loop system. For a negative feedback system, it is minus. So this is the reference input. And so we can call it as, it is a, yeah, this is reference input. Whatever we are feeding back to the system, we can call it as an actual input, right? Right. Suppose if I want to control the speed of a DC motor, so let it be some 1500 RPM as the reference input. So obviously, what the closed loop system has to do, it has to make the system response to stay the reference input, right? So what is the difference between reference input and actual input? Let it be yeah. This is the error signal, right? So we can write error signal as reference input. Reference input is nothing but our desired input minus actual input. So what we want to know is, suppose if I have if I am controlling the speed of a DC motor and say my steady state value means my reference value is at 1000 RPM. Let it be omega t, sorry, n of t. So what we are expecting is what is the expecting response? We are expecting something like this. It has to reach steady state as fast without any oscillations, right? But sometimes there will be some steady state error like this, or it will be like this, plus or minus something will come. It depends upon the system parameter, right? So we need to see how much steady state error is coming to the system, whether it is dependent on any other factors, because we know the transfer function consists of lot of order will be different with respect to the plant. First order plant will be the second order plant will be the third order, something like that, right? So any factor is affecting the steady state value or not. That's why we are going to do. So why we need to analyze the steady state error? Because we need to design a controller in such a way that our steady state error should be zero. It should be very No, you see, suppose I want to control the speed at 1000 RPM, it should not go to some 150 RPM, something like that, right? Because the error is 50 RPM. In whatever may be the case, we have to push this system response to 1000 RPM. That's why we are going for closed loop system. So in order to that, first of all, we need to study, we need to make an analysis on the steady state error. That part only we are doing. Okay. So let E of S be that error, that is a reference input minus actual input. Okay. So according to the transfer function, how we can write this R of S, sorry, E of S. E of S can be written as, what is our reference input? Is R of S minus actual input. What is the actual input coming here? Because Y of S is feeding to the gain block, right? H of S. So what is the value coming here? It will be Y of S multiplied by H of S. So we can write R of S minus H of S multiplied by Y of S. Clear? Okay. What is Y of S from this? From here? Because this error signal is feeding to the forward gain. So the output of this block will be E of S multiplied by G of S, right? So we can rewrite this expression as R of S minus H of S multiplied by Y of S can be written as E of S and G of S. So yeah, correct. So our aim is to find E of S. So move this one to, let's say, so we can write E of S plus G of S, H of S is equal to R of S. So from this, we can write the error signal E of S is equal to R of S divided by 1 plus G of S, H of S. And so this is the expression for error signal. And what is G of S into H of S? We already studied that. If you multiply open loop transfer function with feedback gain, this we can call it as open loop transfer function, right? Open loop transfer function of the system. Clear? Any doubt? So this is the expression for E of S. So if you know E of S, how will you calculate the steady state error? By using initial value theorem, we can find the steady state value, right? By using final value theorem, the steady state error E of t, it is, can be written as, sorry, not E of t, we can represent ESS, steady state error is equal to limit t tends to 0 E of t, right? So according to final value theorem, this can be written as limit S tends to 0, S multiplied by E of S. E of S we know, right? That is R of S divided by 1 plus G of S, H of S. So if you substitute here, we can get the steady state error as limit S tends to 0, S multiplied by R of S divided by 1 plus G of S, H of S. This you keep in mind, okay? Okay, so now we are introducing one new term here in order to analyze this type of a system. Okay, so what do you mean by type of a system? Type of a system. You already seen order of a system, right? Order is the highest order of the denominator polynomial. Now we are introducing one more term, type, we will see what is the importance of type also. So let us consider this transfer function, because in the steady state error, it is s into r of s divided by 1 plus d of s h plus. And what is this? This is the open loop transfer function, right? This is also a transfer function. So let us assume g of s into h of s is equal to s plus 4 divided by s cube plus 3s square plus 5s. So I want to demonstrate what is the type of a system. Say, so this is a strictly proper transfer function, because already we mentioned that for a causal system, m should be less than n. The order of the denominator polynomial should be higher than the order of the numerator polynomial for a causal system, right? That's why your first open loop transfer function g of s and h of s will be like this. So if I take s out in numerator and denominator, not s, sorry, 4, this constant I am taking out. So I want to write in this form, write 0.25s plus 1. And here also I am taking this 5s common out. So the equation will become 1 by 5, that is 0.2 s square, right? 3 by 5 will become 0.6 s plus 1, right? So 4 by 5 is 0.8. So I can write 0.8, 0.25s plus 1. And here one s term will be there. So inside 0.25 s square plus 0.6s plus 1. So I have converted this into a general form. Say this is a k again, and you can see that it started with 1s, right? So now the gain, which is multiplied with s, also changed. Some gain has come here, and you can see that 1 s. What is 1 by s? This means there is a pole at the origin, right? 1 by s means like that. There is a pole at the origin. Okay. So I am writing the general form of this transfer function. In general form, how we can write g of s into h of s is equal to b naught s raised to m plus b1 s to minus 1 plus etc. to b m minus 1 s plus b naught, sorry, bm divided by denominator polynomial can be written as a naught s raised to n plus a1 s raised to n minus 1 plus etc. to a n minus 1 s plus a n. Okay, so this related to this, if I convert to this form, how can I write? One gain will be sitting outside, right? See, so in general I can write that gain as k, and whatever coefficients also will change, right? Previously it was b naught. Now if I convert to that this form, the coefficients also will change. So I can write it as a b naught cap s raised to m. Numerator order is not changing, right? Only the coefficients are changing. Plus b1 cap s power m minus 1 plus etc. up to b m minus 1 cap s plus what about the last one? It becomes 1, right? And similarly, how can we write the denominator? So in denominator there will be 1s power n. It depends upon the order of the system, right? N raised to n, sorry, s raised to n, and the coefficients also will change. Instead of a naught, I can write a naught n, and whether it will become s raised to n, no, right? Because here you can see that it was a third order polynomial. We are taking s out. Now the highest order in this is 2, so I cannot write it as a n. So I am introducing a new term s raised to p. plus A1 S raised to P minus 1 plus etc. up to A n minus 1 K cap. This coefficient is also different. Yes, the last term will be 1. So I can write this open loop transfer function in this form where n is the order, sorry, type of the system. N decides the type of the system, capital N. Hope everyone understood this concept. So we have to take this one denominator S common out, and the power with respect to that S determines the type of the system. So if n equal to 0, we can call that particular system as type 0 system, and for n equal to 1, we can call it as type 1 system. Similarly, for n equal to 2, we can call it as type 2 system, and so on. Okay. So this n determines the type of the system. Okay. Now we will see what is the importance of this type of the system. Okay. So that first we will consider the step input. So we can calculate the steady state error to a unit step reference input. So I am feeding a unit step input as the reference. So I want to know how the steady state error will vary with respect to this type. Okay. So for a unit step input, it is 1. So if you take Laplace transform, it becomes 1 by S. Okay. Now we know the expression for steady state error is limit S tends to 0, S multiplied by R of S divided by 1 plus G of S H of S. So if you substitute here, E of S, steady state error becomes limit S tends to 0. S instead of R of S, put 1 by S. So S and S will cancel. Finally, we will get 1 divided by 1 plus G of S H of S. Okay, this can be written as 1 divided by 1 plus limit S tends to 0, G of S into H of S, and it can be written as 1 divided by 1 plus KV, where KV is called, so now one more term I am introducing, 1 plus KB, where KV is called static position error constant. We will see why it is called static position error constant in the coming class. So error constant. So KV is static position error constant. How will you determine this KV? Where KV is equal to limit S tends to 0, G of S, H of S. Clear? And E of S, steady state error, is equal to 1 by 1 plus KV. So if you are feeding a unit step input as reference input, the corresponding steady state error is equal to 1 divided by 1 plus Kp, where, sorry, not Kv, it is Kp, sorry, it is a position error function, right? It's not Kv, Kp. So where Kp is the static position error constant, which can be calculated using the open loop transfer function, that is limit s tends to 0 g of s h of s. Clear? Now we'll see how the steady state error will vary with respect to type of the system. So I am making a table saying the first column refers to type, second column is the position, static position error constant, third one steady state error. So I'm forming my table here. Now let us consider a first type 1 system. For a type 1 system, what is the value of n? Type 0 system. 0. Okay. So what is the Kp you are expecting? We'll move to this transfer function. Let it be here. From this transfer function. So type 0 means s power 0 will come, right? Right? When s tends to 0, all this inside thing will go to 0. Sorry, just 1 second. I have to connect my charger to the laptop. Yeah, we'll continue our discussion. So what we want to know is we have to find the steady state error for n equal to 0, right? So what is the value you are expecting from the general transfer function? So this is our general transfer function. So open loop transfer function. In numerator k will be there, inside some s time will be there, denominator s power n multiplied by s time, right? So if you put n equal to 0 and calculate the steady state error, what is the value you are expecting? Can you tell?
Okay, sir.
For n equal to 0, g of s h of s becomes k multiplied by some s time divided by s raised to n become s raised to 0 multiplied with some s time, right? So in order to calculate the kp, what we have to do, limit s tends to 0 multiplied with this, right? So if you put s tends to 0, the instant time becomes 0. Here also it will become 0. Finally it will become k by 1. That is k, right? So what is the kp you are getting? It will become k. And finally, what is the value of steady state error? It becomes 1 divided by 1 plus k, where k is the gain, open loop gain of the system. So one thing you understand that if k is large, steady state error will be less, right? But in mathematically it is true, but practically it is not possible because k depends upon the system, right? See, if you consider a closed loop system, there will be a sensor will be there, motor parameters, model will be there. So according to the parameters, some k will be there that we cannot make k as high. So for a type 0 system, there will be some finite value of steady state error, right? That means if I draw the response curve for this, so what is our input? Our input is unit step input. Let it be 1. So I am tracking the response like this. So sub will be somewhat like this. It won't be exactly at 1. There will be some steady state error. It depends upon 1 plus 1 by k. This is for type 0 system. And this will be our ROT. Clear? Hope everyone understood the concept. Now what you can do is you can calculate the steady state error for the type 1 system. Type 1 and type 2. So for type 1 system, g of s, h of s becomes k multiplied by some s time polynomial, and this becomes s raised to 1, and inside some s time, right? So if you put s tends to 0, you will get kp as k by s limit s tends to 0 k by s. So what is limit s tends to 0 k by s? It becomes infinite. So steady state error becomes 1 divided by 1 plus infinite. It will become 0. So if you increase the order, what will happen? If I move to type 2, instead of s, what will happen? Kp becomes limit s tends to 0, 1 by s square will come, right? Because n equal to 2. So in this case also, if you calculate kp, it becomes infinity. Right? So what you understand from this analysis, for type 0 system, there will be some finite error. But if the type is 1 or more than that, obviously the steady state error becomes 0. Okay, so how can we draw the response for this sorry type n equal to 1 or more? We can draw the response like this. Let it be t. This is y of t. So this is our reference input. It is 1 r of t, because in this case steady state error is 0. That is, it will settle exactly at this point. Clear? Okay, then hope no doubts in this. So we'll move to the second case. Means calculate the steady state error for calculate the steady state error to a unit ramp function. We already seen that unit ramp function is a unbounded input, right? Because it will when t tends to infinity, it will go to infinity only, right? But in some cases, we need to track the response for this kind of input variations also. In such case, we have to analyze what is the steady state error when we are feeding a unit ramp function to the plant. Okay. Okay. So we can do the same exercise and find what is the steady state error. Because for a unit ramp function, r of t is equal to t. So r of s becomes 1 by s square. So from this, we can calculate the steady state error as limit s tends to 0, s multiplied by r of s divided by 1 plus g of s h of s. So if you substitute 1 by s square, what will it will become? Limit s tends to 0, 1 divided by s and s square, that will cancel. It will become 1 plus g of s h of s. Right? So this can be again written as limit s tends to 0, 1 divided by s plus s multiplied by g of s h of s. So this can again be written as limit s tends to 0, 1 divided by s g of s h of s. Okay, so like in unit step input, we are introducing one more term here. It's called velocity error constant. Previously, it was static position error constant, KB. Here, this velocity constant, which can be written as limit s tends to 0, s multiplied by g of s h of s. Previously, for Kp, it is limit s tends to 0, g of s multiplied by h of s, right? And you can write steady state error as 1 divided by Kv, which is inversely proportional to the velocity constant. So for a ramp input, the steady state error is 1 divided by Kv. And now the same analysis we will do here also. What will happen when n equal to 0, n equal to 1 and 2. Okay. So we will make one table here, n, kV, and steady state error. So 0, 1, 2. Now tell me, what is the kV you are expecting for a type 0 system? For a type 0 system, it will becomes g of s, h of s is equal to k divided by s raised to 0, right? Okay. Now, in order to calculate kV, we have to multiply it with s. So obviously, kV becomes 0. So what is the steady state error you are getting? Infinite. Right? So if you want to track the response with respect to ramp input, if if the type of the system is 0, the steady state error is infinite, right? It will be very, very, very large. Now you calculate for type 1. What will come for type 1? For type 1, g of s, h of s becomes k divided by s. Right? In this part we don't need to worry because this will become 0, right? So k by s. So you have to multiply it with s. So it will become s k by s, s into g of s, h of s. So s and s will cancel. Finally, you will get k. So what is the steady state error? It is independent of s. Anyway, we'll get kv as k. So steady state error becomes 1 by k. So here you can see that the steady state error depends upon the open loop gain k. So if k is large, we can reduce the steady state error, but in practical case, we cannot tell like that. It depends upon the system. Okay. Now we'll move to type 2. What will happen? Type 2, if you do the same analysis, k, g of s into h of s becomes k divided by s square. And if you want to calculate with s, so it will become 1 by s. Limit s tends to 0, 1 by s will come. So it will become infinite. And this becomes 0. So if you are feeding ramp input to a particular system, if the type is equal to 2 or more, the steady state error is 0. For type 0, the steady state error is infinity, and type 1 it is 1 by k. So you can see that the steady state error for a system with respect to different input depends upon the type of the system, right? Depends upon the type of the system. This steady state error is very, that is the conclusion. So if I want to track a signal goes like a ramp, if I use type 0 system, my steady state error will be very, very, very high. So if the type is 2 or more, the steady state error is very less. That is the meaning. Clear? Hope you understood the concept of steady state error. Anyway, today we will wind up here. We will continue tomorrow. By the time you know what is the importance of this one.